What if the room around you contains directions you cannot point toward, paths you cannot walk along, and spaces so close that they overlap every breath you take, yet remain completely hidden from your senses? It sounds like fantasy, but it is also a serious question in modern physics. The universe may be larger than it appears, not only because it stretches across immense distances, but because space itself may possess more structure than the three familiar directions of left and right, forward and backward, up and down. Before we explore that possibility, take a quiet moment to notice where you are. What time is it there? And from what part of the world are you listening tonight? For most of your life, space has probably seemed simple. You can move across a floor, climb a staircase, lean forward, turn sideways, or look above your head. Every ordinary journey can be described using three independent directions. A point can be located by saying how far it is from you from side to side, how far ahead or behind, and how far above or below. These three measurements are enough to describe the position of a chair, a star, a drifting grain of dust, or your own body resting beneath a blanket. This familiar three-dimensional world feels so complete that imagining another direction seems almost impossible. Where could an extra direction go, when all possible movement already appears accounted for? In mathematics and physics, a dimension is not necessarily a mysterious realm or a separate universe. At its most basic, a dimension is an independent quantity needed to specify a position or describe how something can change. A straight line has one spatial dimension because a point on that line requires only one number to locate it. A flat surface has two dimensions because two numbers are needed. A room has three. The idea becomes more subtle when physicists describe events rather than objects, because an event has not only a location but also a moment. To say where something happened is incomplete unless we also say when. This is why modern physics treats time as part of a four-dimensional structure called spacetime. Time, however, does not feel like an ordinary spatial direction. You can choose to move north or south, upward or downward, but you do not seem free to turn around and stroll back toward yesterday. Time also enters the equations of relativity differently from the three dimensions of space. Still, space and time are deeply connected. The amount of time measured between two events can depend on motion, and the measured length of an object can depend on the observer's speed. These effects are usually tiny in everyday life, but at velocities close to the speed of light, they become impossible to ignore. Nature does not maintain a perfectly separate clock and ruler. Instead, it combines them into the geometry of spacetime. This realization already asks us to move beyond ordinary intuition. Human senses did not evolve to understand objects traveling near light speed or clocks ticking differently in different gravitational fields. They evolved to help our ancestors walk, reach, balance, avoid danger, and recognize familiar surroundings. Our brains are remarkably good at constructing a useful picture of the world. But usefulness is not the same as completeness. We see only a narrow band of electromagnetic radiation, which we call visible light. We hear only a limited range of vibrations. We do not directly sense magnetic fields, neutrinos, curved spacetime, or the constant quantum activity underlying matter. Reality has never been limited to what the nervous system can immediately reveal. Hidden dimensions, if they exist, would belong to this broader category of reality beyond direct perception. They would not necessarily be far away. An extra spatial dimension could, in principle, be present at every point around you. It might be involved in the behavior of particles, force, or gravity, without offering an obvious direction for your hand to move. This can seem contradictory, but only because the word dimension often brings to mind a large open direction, like the height of a mountain or the width of a valley. Physicists also consider dimensions that may be compact, tightly curved, or confined to scales so small that ordinary objects cannot travel through them in any noticeable way. To understand how a direction can exist without being obvious, imagine looking at a thin cable from a great distance, from far away. The cable appears to be a one-dimensional line. A small creature moving along it could travel forward or backward. At that scale, those seem like the only possibilities. But as you move closer, you notice that the cable has a circular surface. A tiny creature could also crawl around its circumference. That second direction was always present. Yet it was difficult to detect from far away because it curled back on itself over a very small distance. The cable was not truly one-dimensional. It only appeared that way when observed at a scale much larger than its thickness. This simple image is often used to introduce the idea of compact dimensions. A hidden spatial direction might be less like a vast highway, and more like the tiny circular direction around the cable. At every position in familiar space, there could be an additional structure curled into an extremely small shape. Moving through ordinary distance would be like travelling along the length of the cable, while moving through the hidden dimension would mean circling around its narrow surface. If that circumference were unimaginably small, even smaller than anything current instruments could resolve, the universe would appear three-dimensional under all ordinary conditions. The comparison is useful, but it should not be taken too literally. A real extra dimension would not need to look like a tiny visible circle attached to space. Its geometry could be far more complicated. It might be folded into a shape with many loops and connections, or it might be large while ordinary matter remains confined to a smaller region within it. Different theories propose different possibilities. What they share is the suggestion that the dimensions we perceive may be only the accessible portion of a deeper geometry. The mathematics can describe these possibilities clearly, even when the human imagination struggles to form a picture of them. This difference between mathematical understanding and visual imagination is important. You do not need to picture a four-dimensional object perfectly in order to reason about it. No one can directly visualize curved spacetime in the full way it appears in Einstein's equations. Yet those equations make precise predictions. Scientists often work with structures that cannot be represented faithfully by a three-dimensional mental image. They use relationships, measurements, symmetries, and equations instead. Mathematics allows the mind to move carefully through spaces that the eyes could never display. In this sense, hidden dimensions are not considered scientific merely because they sound fascinating. They become scientific when they appear in theories that can be analysed and, at least in principle, tested. The idea of unseen dimensions is older than many of the theories now associated with it. Mathematicians studied spaces with four or more dimensions long before physicists seriously proposed that nature might contain them. In mathematics, adding dimensions is straightforward. A point in a five-dimensional space requires 5 coordinates instead of 3. The difficulty comes when we ask whether any of those additional coordinates correspond to physical directions in the real universe. Mathematics permits countless possible worlds. Physics must determine which mathematical description, if any, matches observations. A beautiful model may still be wrong, and an elegant extra dimension may remain only a possibility until nature provides evidence. Even the 3 dimensions we experience invite deeper questions. Why are there exactly 3 large spatial dimensions? Why not 2, 4, or 7? Could stable planetary orbits exist in a universe with more large dimensions? Could atoms remain intact? Some mathematical studies suggest that familiar physical stability depends strongly on dimensionality. Although such arguments involve assumptions about how forces behave, in 3 spatial dimensions, gravity and electromagnetism weaken with distance in a particular way. In a different number of large dimensions, those laws would change their form, the structures necessary for stars, chemistry, and living organisms might then behave very differently or fail to persist. This does not prove that space must have only 3 dimensions. It suggests instead that 3 extended dimensions may be especially suitable for the complex structures we observe. Additional dimensions could still exist if they are hidden, compact, or otherwise prevented from changing large-scale physics too dramatically. They might influence the universe most strongly at extremely short distances or very high energies, conditions far beyond everyday experience. This is one reason extra dimensions appear in attempts to understand the smallest building blocks of nature. At ordinary scales, space would remain comfortably three-dimensional. At deeper scales, its structure might become richer, much as a smooth thread reveals twisted fibers when examined closely. The scale at which hidden dimensions might appear is difficult to grasp. Some theories place them near the Planck length, roughly 10 to the power of minus 35 meters. This is vastly smaller than an atomic nucleus, which is itself already tiny beyond ordinary visualization. The Planck scale is not simply the smallest proven length in nature, but it marks a region where current theories suggest that quantum effects of gravity may become important. Existing particle accelerators cannot directly examine distances anywhere near that small. If extra dimensions are compactified at such scales, they may remain hidden not because they are supernatural, but because the energy required to probe them is far beyond present technology. Yet physicists have also explored models in which extra dimensions could be much larger than the Planck scale. In some proposals, they might be as large as fractions of a millimeter, while ordinary particles remain unable to enter them. Gravity, however, might spread through those additional directions. This could help explain why gravity appears extraordinarily weak compared with the other fundamental interactions. A small magnet can lift a metal object against the gravitational pull of the entire Earth. Perhaps gravity is not inherently so weak. Perhaps part of its influence escapes into a larger dimensional space that we do not directly inhabit. This remains hypothetical, but it leads to experiments that test gravity at very short distances. No confirmed experiment has revealed an extra spatial dimension. Measurements so far are consistent with a universe that behaves as though it has 3 large spatial dimensions and 1 time dimension. This absence of evidence does not eliminate every possible model, because many versions predict effects too subtle or too energetic for current instruments. But it does place limits on what hidden dimensions could be like. They cannot simply alter nearby gravity or particle behavior in ways that experiments would already have detected. Each new measurement narrows the range of possibilities, turning a broad idea into a more disciplined scientific question. There is something quietly beautiful about this process. Science does not ask us to believe in hidden dimensions because they inspire wonder. It asks whether the idea explains known facts, connects theories, and survives attempts to prove it wrong. The mystery remains open, suspended between mathematical possibility and physical evidence. Around you, space still feels ordinary. The walls keep their distance, the ceiling remains above, and every object rests within the familiar geometry of daily life. Yet beneath that calm appearance, physics allows the possibility that each point contains more than the senses can enter, and that the universe may extend in directions for which the human mind has never needed a name. To imagine a hidden dimension, it helps to begin with a world simpler than our own. Picture a perfectly flat surface stretching endlessly in every direction, like an infinite sheet of paper with no thickness at all. Now imagine intelligent beings living entirely within that surface. They can move left and right, forward and backward, but the ideas of above and below do not exist in their experience. Their bodies, olmes, and instruments are all flat. Light travels only across the surface, so they cannot look outward into the third dimension. To them, their two-dimensional world is not a slice of something larger. It is the whole of reality, complete and apparently self-contained. A flat creature would have difficulty imagining our three-dimensional space for the same reason we struggle to imagine a fourth spatial direction. It could understand two perpendicular directions because both are available for movement. But when asked to point in a direction perpendicular to both, it would find no remaining option within its world. Any line it draws must lie on the surface. We might tell the creature that another direction exists, one leading out of the sheet. Yet every word we use would refer to an experience it has never had. The problem would not be a lack of intelligence. It would be a limit created by the structure of perception itself. Suppose you gently lower a three-dimensional sphere through this flat world. The inhabitants cannot see the whole sphere because most of it lies outside their space. They can observe only the portion intersecting their surface. At first, when the sphere barely touches the plane, they see a tiny point. That point grows into a small circle, then a larger one, until the sphere's widest region passes through. Afterward, the circle shrinks again and finally disappears. To the flat observers, a mysterious object seems to appear from nowhere, change size without understandable cause, and vanish just as strangely. Yet from our perspective, nothing supernatural has happened. They have seen only a changing cross-section of a simple object moving through a higher dimension. This thought experiment offers a gentle way to consider how a higher dimensional object might appear to us. If a four-dimensional shape passed through our three-dimensional space, we might perceive a sequence of changing three-dimensional forms rather than the entire object at once. Something could seem to appear, transform, divide, reconnect, and disappear as different portions intersected the space accessible to us. Such images are mathematically meaningful, but they should not be confused with evidence that these events occur in nature. They simply demonstrate how incomplete perception can make an ordinary higher dimensional process look mysterious to a lower dimensional observer. Another way to approach higher dimensions is through shadows. A three-dimensional object can cast a two-dimensional shadow. A cube, depending on its orientation, may produce the shadow of a square, a rectangle, or a more complex arrangement of overlapping shapes. The shadow contains information about the cube, but not all of it. Different objects can cast similar shadows, and a single object can cast many different shadows as it turns. In a comparable way, a four-dimensional object could have a three-dimensional projection. We might study that projection mathematically, even though it would distort or hide aspects of the original form. The best-known four-dimensional analogue of a cube is called a tesseract. A line segment can be created by connecting 2 points. A square can be imagined as 2 parallel line segments connected at their ends. A cube can be imagined as 2 parallel squares connected at corresponding corners. Following the pattern, a tesseract can be described as 2 cubes displaced along a fourth spatial direction and connected at corresponding vertices. We cannot place a complete tesseract inside ordinary three-dimensional space without distortion, but we can draw projections of it. These often look like a smaller cube nested inside a larger cube, with lines joining their corners. Such drawings are not literal photographs of four-dimensional objects. They are more like perspective sketches of a cube on flat paper. When you draw a cube, some edges appear shorter, parallel lines may seem to converge, and surfaces overlap. The two-dimensional page compresses three-dimensional information. A tesseract projection compresses four-dimensional information into 3 dimensions, and then perhaps again onto a two-dimensional screen. The result can look confusing. But confusion does not mean the concept is inconsistent. It means our representation has lost information while moving through lower dimensions. Rotation provides another useful comparison. In 2 dimensions, a square can rotate within its plane. In 3 dimensions, it can also rotate out of that plane, exposing angles that a flat observer could not anticipate. A 3-dimensional cube can rotate around several axes, but a 4-dimensional cube would have additional kinds of rotation unavailable in ordinary space. When a projected tesseract appears to turn inside out, its parts expanding and passing through one another. The strange motion may be caused by a smooth rotation in 4 dimensions. The apparent distortion comes from viewing that motion through a reduced projection. A lower dimensional world would also experience boundaries differently. Imagine drawing a closed circle around a flat creature. Within its two-dimensional universe, the circle forms a complete wall. The creature cannot leave the enclosed region without crossing the boundary. But you, able to move through the third dimension, could lift the creature over the circle and place it outside without passing through the line. To the creature, this escape would seem impossible. In the same way, a being with access to a fourth spatial dimension could theoretically move around a closed three-dimensional boundary without passing through its surface. A sealed room illustrates the idea. Every path available to us passes through the walls, floor, or ceiling, but those barriers enclose only the directions we know. A four-dimensional traveller, if such a being were physically possible, might step around the room through an additional spatial direction and re-enter at another point. It could remove an object from a locked container without opening it, just as you could lift a coin from inside a circle drawn on paper. Again, this is not a claim that hidden beings are entering rooms. It is a geometrical consequence of adding another independent direction. Higher dimensional geometry can also change how knots behave. A knot in a string is difficult to remove because the string cannot pass through itself in three-dimensional space. If the string had access to a fourth spatial direction, one segment could move around another without crossing it in the familiar sense. Many knots that are stable in three dimensions could be untied effortlessly. By contrast, structures that seem simple in our space may possess more complicated higher dimensional analogues. Mathematics uses these ideas to study topology, the properties of shapes that remain unchanged under continuous stretching and bending. Topology asks questions that are less concerned with exact distances and more concerned with connection. A coffee cup with one handle and a ring-shaped donut are considered topologically similar because one can be smoothly reshaped into the other without tearing or gluing. Both contain a single hole. A sphere is different because it has no such hole. In higher dimensions, possible forms become far more varied. Hidden dimensions, if compactified, would not need to be simple circles. They could have intricate topologies containing multiple loops, tunnels, and connected regions. This matters because the shape of a hidden dimension could influence the physics we observe. Imagine a musical instrument. The tones produced by a string depend on its length, tension, and allowed patterns of vibration. A drum head supports different modes depending on its shape and boundary. In theories with extra dimensions, fields or tiny fundamental objects may vibrate within the hidden geometry. The permitted patterns could appear in our three-dimensional world as different particle masses, charges, or interactions. The small shape would not merely be an invisible location, it could help determine the character of visible matter. Even familiar objects show how hidden structure can shape large-scale behavior. A sheet of paper appears smooth from across a room, but under magnification, it becomes a landscape of tangled fibers. A metal surface may look continuous, though it is made of atoms arranged in a lattice. Water seems uniform, yet its molecules are constantly moving and forming fleeting patterns. In each case, a deeper structure controls properties observed at larger scales. The strength of paper, the conductivity of metal, and the flow of water emerge from details too small to see directly. Extra-dimensional models extend this principle into geometry itself. What appears to be empty three-dimensional space might possess a microscopic architecture at every point. The hidden directions could be so small that travelling across a room leaves them unnoticed. Just as walking along a distant road does not reveal the rounded surface of each grain of asphalt, yet particles operating at sufficiently short distances might respond to that architecture. Their possible states could depend on it. Even though human bodies and ordinary instruments remain effectively confined to the large dimensions, there is another possibility. Hidden dimensions may not be small. Instead, Matter and light might be restricted to a three-dimensional region within a larger space. Imagine insects living on the surface of a pond. The water extends beneath them, but if the insects can move only along the surface, their world behaves as two-dimensional. Waves and other effects may travel through the surrounding volume even when the insects cannot. Some theories suggest that our observable universe could be similarly embedded within a higher dimensional environment, with most familiar particles confined to a three-dimensional layer. Our imagination naturally tries to picture this layer as a sheet floating inside a larger room. That picture is helpful, but it can also mislead. The higher dimensional space would not necessarily lie somewhere beyond the visible sky. It might be present at every point, separated from us by direction rather than distance. Looking farther into the universe would not automatically reveal it. Just as a flat creature cannot find the third dimension by travelling farther across its plane, it could journey forever and remain within the same surface because the missing direction is perpendicular to every path it knows. This distinction between distance and dimension is subtle. A hidden dimension is not simply a remote region waiting beyond the edge of the observable universe. The observable universe is limited by how far light has travelled since the early cosmos. While dimensionality describes the independent directions available to space itself, something can be extremely distant, yet still lie within the same three dimensions. An extra dimension, by contrast, could be locally near while remaining inaccessible. Every point in your room might possess it, yet no ordinary motion would carry you through it. Human intuition resists such ideas because the brain builds its model of space from movement and sensation. As infants, we learn depth by reaching, crawling, focusing our eyes, and watching objects change as we approach. Our understanding of three dimensions is not given as an abstract theorem. It is assembled from experience. We have no comparable sensory history for a fourth spatial direction. We cannot turn our heads toward it or watch an object recede along it. The absence of intuition is therefore expected, not evidence that the idea is meaningless. Mathematicians overcome this limit by replacing visualization with patterns. A point in four-dimensional space can be labelled by four coordinates. Distances can be calculated using extensions of familiar geometry. Shapes can be defined by equations, and rotations can be described using precise transformations. These objects follow consistent rules even when they cannot be fully imagined. In the same way, you may understand a piece of music through notation without hearing every possible performance, or follow the logic of a map without physically visiting every road. Still, thought experiments remain valuable because they create bridges between mathematics and experience. The flat world, the passing sphere, the folded sheet, and the shifting shadow do not reveal what extra dimensions truly look like. Instead, they teach humility. They show that an observer can live inside a reality whose full structure remains hidden, and that partial evidence may appear strange when interpreted within too narrow a framework. What seems impossible from inside one set of dimensions may become simple when viewed from a larger geometry. This lesson extends beyond hidden dimensions. Science repeatedly discovers that nature does not organize itself according to human expectation. The earth moves, though the ground feels still. Time flows at different rates, though seconds seem universal. Particles behave like waves. Empty space carries fields, and gravity reflects the curvature of space-time. Each discovery has required the mind to loosen its attachment to ordinary experience while remaining anchored to measurement. For now, hidden dimensions remain possibilities rather than established features of nature. The thought experiments tell us how such dimensions could escape perception, but they do not tell us whether the universe actually contains them. To move from imagination toward physics, we must ask why scientists introduced additional dimensions in the first place. The answer begins with a transformation in our understanding of gravity. When space ceased to be a silent emptiness and became a flexible participant in the motion of matter, light, planets, and stars, for a long time, Space was imagined as a quiet stage on which the universe performed. Stars moved across it, planets travelled through it, and light crossed it. But space itself was thought to remain unchanged. It was simply there, an invisible background stretching between objects. Time seemed equally separate, flowing at the same rate everywhere. This picture worked well for ordinary life and for much of classical physics. Yet as scientists examined light, motion, and gravity more carefully, the old stage began to dissolve. Space and time were not passive after all. They could stretch, bend, and respond to matter, and their shape could guide the motion of everything within them. The first major step came with special relativity. Albert Einstein began from two ideas. The laws of physics should appear the same to observers moving at constant speeds, and the speed of light in empty space should be measured as the same by all such observers. These principles sound simple, but together they change the meaning of distance and duration. Two observers moving differently may disagree about whether events happened at the same time. They may measure different lengths and different intervals between moments. Neither observer is necessarily mistaken. Space and time adjust together so that the deeper structure of physical law remains consistent. This union of space and time is called spacetime. You can imagine every event as a point within it, defined by 3 coordinates of space and 1 coordinate of time. Your present moment is one such event. A flash from a distant star is another. The movement of an object becomes a path through space-time, sometimes called a world line. A person sitting still in a room is not motionless in this broader sense, because that person continues moving through time. A beam of light follows a different kind of path, shaped by the special relationship between distance and duration built into relativity. Special relativity dealt with observers moving smoothly, and with regions where gravity could be ignored. Gravity remained a separate puzzle. In Newton's description, every mass attracts every other mass through a force acting across space. The theory was extraordinarily successful, explaining falling objects, planetary orbits, tides, and the motion of comets. Yet it did not explain how gravitational influence travelled or how it could fit naturally with the finite speed of light. If the sun were somehow moved, Newton's equations seemed to imply that Earth would respond immediately. Relativity suggested that no physical influence should travel infinitely fast. Einstein's search for a deeper theory began with a quiet observation about falling. Imagine standing inside a sealed elevator far from planets and stars. If the elevator accelerates upward, you feel pressed toward the floor. An object released from your hand falls downward relative to the elevator. Now imagine the elevator resting on Earth. You feel weight, and the released object again falls toward the floor. From inside the sealed cabin, these situations can appear remarkably similar. Acceleration and gravity are deeply connected. This idea became known as the equivalence principle and served as a doorway into general relativity. Now imagine that the elevator is freely falling. Inside, you and every loose object fall together. For a brief time, you appear weightless, even though gravity has not vanished. Astronauts orbiting Earth experience something similar. They are not beyond Earth's gravity. They are continuously falling around the planet. Their spacecraft, bodies, and equipment all share almost the same motion, creating the sensation of floating. Gravity, Einstein realized, might not be an ordinary force pulling objects away from their natural paths. It might instead reflect the shape of space-time itself. In general relativity, matter and energy curve space-time. Objects then move along the straightest possible paths within that curved geometry. These paths are called geodesics. On a flat sheet, a geodesic is an ordinary straight line. On the curved surface of Earth, the nearest equivalent is a great circle route, like the path followed by many long-distance flights. A traveller can follow such a route without feeling a sideways force. even though the path looks curved when drawn on a flat map. In a similar way, Earth follows a natural path through curved spacetime around the Sun. The familiar image of a heavy ball resting on a stretched rubber sheet is often used to illustrate this. The ball creates a depression, and smaller balls roll around it. The picture captures the idea that mass changes geometry, but it has serious limits. It uses Earth's gravity to explain gravity, and the rubber sheet has only 2 visible dimensions, while real spacetime has 4. It can also suggest that objects are simply pulled into a downward pit. In reality, the curvature involves both space and time, and the time component is especially important in determining planetary motion. A more careful image is to think of clocks and rulers changing their relationships in the presence of mass. Near a massive object, time passes more slowly relative to regions farther away. Distances are also shaped differently from those in flat space. A planet travelling through this geometry follows the path that requires no additional force from its own perspective. It is moving freely, yet the path appears curved when viewed across time. What we call gravitational attraction emerges from this geometry. The Sun tells spacetime how to curve, and curved spacetime tells Earth how to move. This description is not merely philosophical. General relativity produces measurable predictions. It explained a small irregularity in the orbit of Mercury that Newtonian gravity could not fully account for. It predicted that light should bend when passing near a massive object, a phenomenon now observed in many settings. It also predicted gravitational time dilation. Clocks at different gravitational potentials tick at slightly different rates. This effect is so real that satellite navigation systems must account for relativity. Without such corrections, their calculated positions would quickly become inaccurate. Gravity also changes the frequency of light. Light climbing away from a massive body loses energy and shifts toward longer wavelengths, an effect known as gravitational redshift. Light descending into a gravitational field shifts toward shorter wavelengths. These changes do not mean that photons become tired during a journey. They reflect differences in how time and energy are measured at different locations in curved spacetime. Again, geometry is not an abstract decoration. It influences the behavior of clocks, signals, matter, and radiation in ways that can be precisely tested. The curvature of spacetime becomes extreme around black holes. When enough mass is compressed into a sufficiently small region, spacetime bends so strongly that a boundary forms beyond which light cannot escape. This boundary is called the event horizon. A black hole is not an ordinary hole in space, nor is it a tunnel proven to lead elsewhere. It is a region where spacetime geometry creates paths that all point deeper inward. From far away, an infalling object appears to slow near the horizon, while the object itself crosses that region in finite time according to its own clock. General relativity also predicted gravitational waves, ripples in spacetime produced by accelerating masses. When massive objects such as black holes or neutron stars orbit one another, they disturb the geometry around them. These disturbances travel outward at the speed of light, carrying energy. In 2015, instruments directly detected gravitational waves from merging black holes, confirming a century-old prediction. The measurement was extraordinarily delicate. The passing wave changed the lengths of detector arms by a fraction far smaller than the width of a proton. Yet the signal matched relativity with remarkable precision. Once space and time became dynamic, asking about additional dimensions no longer seemed like a purely mathematical game. If geometry could act as gravity, perhaps other forces might also be expressions of geometry in a larger spacetime. This possibility inspired one of the earliest physical theories of an extra dimension. In the early 20th century, Theodore Kaluza considered extending general relativity from 4 dimensions to 5. The 5th dimension was spatial. Although unlike the familiar 3, it was not visible in ordinary experience. When Kaluza wrote Einstein's gravitational equations in 5 dimensions and then examined how they would appear from a four-dimensional viewpoint, something remarkable emerged. Part of the higher dimensional geometry resembled ordinary gravity, while another part resembled the equations of electromagnetism. A single geometric framework seemed able to contain both gravitational and electromagnetic fields. The suggestion was elegant. What appears to us as electromagnetism might be a shadow of geometry in an unseen dimension. Just as gravity is the geometry of spacetime, the idea raised an immediate question. If a fifth spatial dimension exists, why do we not move through it or detect it? Oscar Klein later proposed that the dimension might be compactified, curled into a tiny circle at every point in space. From a great distance, a thin hose looks like a line, though an ant can move both along its length and around its circumference. In the same way, space might appear three-dimensional at large scales while possessing a tiny circular direction at small scales. The extra dimension would be present everywhere but hidden by its minute size. Kaluza-Klein theory did not become a complete description of nature. Its simplest form could not accurately explain all known properties of electromagnetism and matter, yet it introduced a profound possibility. Forces might emerge from the shape of dimensions. A field that appears fundamental in four-dimensional spacetime could be a geometric effect of a higher dimensional world. This idea would return decades later in more elaborate theories, including attempts to unify all known particles and interactions within a single mathematical structure. The success of general relativity made geometry central to physics, but another revolution was unfolding at the same time. Quantum mechanics revealed that matter and radiation behave in ways unlike familiar objects. Particles can exist in superpositions, display wave-like interference, and possess probabilities rather than perfectly defined classical paths. Quantum theory describes atoms and elementary particles with extraordinary accuracy. General relativity describes gravity and the large-scale universe with equal power. Yet the two frameworks are built on different principles and resist being combined in extreme conditions. This conflict becomes important near the center of black holes and in the earliest moments of the universe, where strong gravity and quantum effects should both matter. General relativity treats spacetime as a smooth geometry. Quantum theory suggests that fields fluctuate and that physical quantities can become uncertain. When physicists try to treat gravity like other quantum forces using straightforward methods, the calculations often produce uncontrollable infinities. This does not mean either theory is useless. It means that both may be incomplete parts of a deeper description. Extra dimensions entered this search because they offered new ways to organize particles, force, and geometry. A higher dimensional theory might appear complicated from our limited viewpoint, while being simpler in its full form. Just as a single three-dimensional object can cast many different two-dimensional shadows, one higher dimensional structure might appear as several distinct forces and particles when observed from four-dimensional spacetime. The variety of nature could emerge from a more unified geometry that remains hidden from direct perception. There is an important caution here. Elegance does not guarantee truth. Many theories can produce beautiful mathematical relationships without describing the actual universe. General relativity earned its place because its predictions survived repeated experiments. Extra-dimensional theories must meet the same standard. They must explain observations, avoid contradicting existing evidence, and ideally predict something new that can be tested. Until then, additional dimensions remain possible ingredients in a deeper theory, not established parts of physical reality. Still, general relativity changed the question forever. Space was no longer merely the emptiness between things. It had structure, responded to energy, carried waves, and shaped the passage of time. Geometry had become a physical actor. Once that door opened, it was natural to wonder whether the geometry we observe is only part of a larger arrangement. Perhaps the three dimensions surrounding us are the broad, extended directions of a far more intricate space. Perhaps other directions curl quietly beneath the reach of our senses. waiting not beyond the stars, but within the architecture of every point. By the middle of the 20th century, physicists had learned to describe nature using two remarkably successful frameworks. General relativity explained gravity as the curvature of spacetime, while quantum theory described particles and forces through fields, probabilities, and discrete exchanges of energy. Yet the two descriptions did not fit naturally together. When researchers tried to apply quantum methods to gravity under extreme conditions, the mathematics often became unstable. Extra dimensions offered one possible path forward. They suggested that the particles and forces we see might not be separate ingredients placed into the universe one by one, but different expressions of a deeper geometric structure hidden beneath ordinary space. This possibility became especially important with the development of string theory. In the standard picture of particle physics, electrons, quarks, and other elementary particles are treated as point-like objects with no measurable internal size. String theory replaces these idealized points with extremely tiny one-dimensional objects. A string may be open like a short thread or closed like a loop. Its different patterns of vibration can appear, from our perspective, as particles with different masses, charges, and other properties. In this picture, an electron and a photon would not be made from different substances. They would be different notes played by the same fundamental kind of object. The musical comparison is useful because a violin string can vibrate in many distinct ways. One pattern produces a lower note, another a higher one, and more complicated patterns produce overtones. A fundamental string would also possess allowed modes of vibration, though at scales far beyond direct observation. Each mode would carry a particular amount of energy and behave like a specific particle. The hope is that the variety of matter might emerge from a single underlying principle. Rather than asking why nature contains so many unrelated particles, one could ask why strings are allowed to vibrate in these particular ways. String theory attracted attention partly because one of its vibration modes behaves like a quantum particle of gravity. This hypothetical particle is often called the graviton. In many earlier attempts to quantize gravity, troublesome infinities appeared and could not be removed consistently, because strings are extended rather than perfectly point-like. Their interactions are spread over a tiny region instead of occurring at an exact mathematical point. This softens certain calculations and makes a quantum description of gravity more manageable. The result is not a completed, experimentally confirmed theory, but it shows why strings became central to many efforts to unite gravity with quantum mechanics. The mathematics of string theory, however, does not work consistently in only 3 spatial dimensions and 1 time dimension. Depending on the version, it requires additional spatial dimensions. The earliest bosonic form required 26 total dimensions, though it contained serious problems and did not describe known matter realistically. Later superstring theories reduced the requirement to 10 dimensions, 9 dimensions of space and 1 of time. A broader framework known as M-theory is usually described using 11 dimensions. These numbers are not added merely for mystery. They arise from mathematical conditions needed to prevent internal contradictions. This immediately returns us to the central question. If a theory requires 9 or 10 spatial directions, why do we experience only 3? The usual answer is that the additional dimensions could be compactified. During the universe's early history, 3 spatial dimensions may have expanded to enormous scales while the others remained tightly curled. The hidden directions could be present at every location, but their size might be so small that ordinary movement never reveals them. A person crossing a room would travel through the large dimensions while remaining unaware of the intricate microscopic space folded into each point along the way. A tiny compact dimension changes what kinds of motion are possible. Imagine a particle moving around a circular direction so small that it quickly returns to where it began. Quantum mechanics does not allow every possible motion around that circle. Only certain patterns fit smoothly, much like standing waves on a string. Each allowed pattern carries a particular amount of momentum and therefore a particular amount of energy. to an observer who cannot see the hidden circle. These states may appear as a family of particles with increasing masses. These hypothetical copies are often called Kaluza Klein modes. The smaller the hidden circle, the more energy is required to excite motion around it. If the compact dimension is extremely tiny, the first detectable Kaluza Klein mode may be far beyond the reach of current particle accelerators. At low energies, particles remain in their simplest state and the dimension appears invisible. This is similar to a narrow pipe whose circular direction matters to a tiny insect but not to a distant observer. Only when a probe has enough resolution or enough energy does the hidden structure begin to influence measurable behavior. In realistic string models, compact dimensions are usually more complicated than circles. They may be curled into intricate six-dimensional shapes, often associated with structures called Calabi-Yau manifolds. These spaces cannot be pictured faithfully by the human mind, but their properties can be studied mathematically. They may contain holes, loops, intersecting cycles, and curved regions. The exact geometry matters because it influences how strings can vibrate. Different compact shapes can produce different collections of particles. Force, mass, and symmetries in the large dimensions we observe. This creates both promise and difficulty. The promise is that the laws of particle physics might emerge from geometry, features that seem arbitrary, such as why a particle has a certain charge or why a force has a particular symmetry, could reflect the shape of hidden dimensions. The difficulty is that there are an enormous number of mathematically possible compact geometries. Each may generate a different low-energy universe. Researchers often refer to this vast set of possibilities as the string landscape. Finding the configuration that reproduces our universe is not like solving one simple equation. It is more like searching an immense library for a book whose language is only partly known. The shape of the hidden space may not remain fixed automatically. Compact dimensions could expand, contract, twist, or change unless some physical mechanism stabilizes them. The parameters describing their size and shape are often called moduli. If these moduli varied freely, the values of particle masses and forces might change over time, contradicting observation. String models therefore require ways to lock the hidden geometry into a stable or slowly changing form. Fields, fluxes, branes, and quantum effects may help accomplish this, but the process is mathematically difficult and not uniquely determined. Compactification also raises questions about the earliest universe. Perhaps all spatial dimensions began small and highly energetic, for reasons not yet fully understood. 3 of them may have expanded while the others remained compact. Some models suggest that strings moving through space could allow only a limited number of dimensions to grow large. Others connect the process with inflation, 2-phase transitions, or the behavior of fields in the early cosmos. None of these explanations has been confirmed. They are attempts to understand not only whether hidden dimensions exist, but why exactly 3 dimensions became spacious enough for galaxies, planets, and life. The number 3 has unusual physical consequences. In 3 spatial dimensions, waves spread over the surface of expanding spheres, and the strength of forces such as gravity follows the familiar inverse square pattern at large distances. Stable orbits and long-lived atomic structures depend partly on these relationships. In more than 3 large spatial dimensions, gravity would generally weaken with distance in a different way. Planetary orbits might become unstable under simple extensions of known laws. This does not prove that only 3 dimensions can support complexity, but it suggests that dimensionality is closely tied to the possibility of persistent structure. String theory also introduces supersymmetry, a proposed relationship between 2 broad classes of particles. Matter particles, known as fermions, would have partners among force-carrying particles, known as bosons, and vice versa. Supersymmetry helps make string calculations consistent and may stabilize certain physical quantities. Yet no supersymmetric partner particle has been experimentally confirmed. If supersymmetry exists, it may be broken at energies higher than current experiments can easily reach. Its absence at accessible scales places important constraints on the simplest models but does not eliminate every version. There are several mathematically consistent superstring theories, once thought to be separate. During the 1990s, physicists discovered that these theories are connected by dualities. A theory describing a very small, compact dimension might be mathematically equivalent to another describing a large one. Strong interactions in one description may correspond to weak interactions in another. These surprising relationships suggested that the theories were different views of a deeper framework. Theory emerged as a name for that broader structure, though its complete formulation remains unknown. One of the most striking dualities is called T-duality. In ordinary geometry, a circle with a very small radius seems clearly different from one with a very large radius. In string theory, however, strings can carry ordinary momentum around a circular dimension and can also wrap around it. Momentum becomes harder to excite as the circle shrinks, while winding becomes easier. Under certain conditions, exchanging these two kinds of behavior makes a tiny circle physically equivalent to a large one. At the deepest scale, the usual distinction between small and large may not be as absolute as everyday intuition suggests. This does not mean that a room could suddenly become microscopic or that ordinary distances are illusions. T-duality applies within specific theoretical settings involving fundamental strings and compact directions. Its significance is more subtle. It suggests that geometry itself may emerge from deeper relationships, rather than serving as the final foundation of physics. The size and shape of space might not always be fundamental properties. They may be effective descriptions that become meaningful only at scales much larger than the strings and quantum processes beneath them. Another major idea is that dimensions can be hidden not only by being small, but by controlling which particles are free to move through them. In some models, ordinary matter is confined to a lower dimensional surface. While gravity can travel through a larger surrounding space, such surfaces are called branes, a word derived from membrane. A one-dimensional string is a type of brane, and higher dimensional branes can have 2, 3, or more spatial dimensions. Our observable universe might, in principle, be associated with a 3-dimensional brane embedded in a higher dimensional bulk. This picture offers a different explanation for the apparent weakness of gravity. Electromagnetism and the nuclear forces may remain confined to our brain, while gravity spreads into additional dimensions. From our perspective, its strength would seem diluted. The idea has inspired models with extra dimensions much larger than the Planck length, perhaps even large enough to affect experiments at sub-millimeter scales. Precision tests have searched for deviations from the inverse square law of gravity at short distances. So far, no convincing deviation has been found, placing limits on the size and form of any such dimensions. Other models use strongly curved extra dimensions rather than large flat ones. In these scenarios, spacetime may be warped in a way that changes how gravity behaves across the hidden direction. A relatively modest separation in the extra dimension could correspond to enormous differences in observed energy scales. This might help explain why gravity is so much weaker than the other forces without requiring every hidden dimension to be unimaginably tiny. Again, these ideas are theoretical. Their value depends on whether they eventually lead to distinctive predictions that experiments can test. It is easy to become lost among strings, branes, manifolds, dualities, and compactification. Yet the central idea remains simple enough to hold quietly in the mind. What we call particles may reflect patterns of motion in unseen directions. What we call forces may reflect the geometry of a space larger than the one we directly perceive. The hidden dimensions would not be decorative additions. Their shape, size, and accessibility could determine the behavior of the visible universe, much as the shape of an instrument determines the music it can produce. Still, no experiment has confirmed string theory or identified a compact extra dimension. The relevant scales may be far beyond present technology, and the theory currently permits many possible low-energy outcomes. Some physicists view its mathematical unity as evidence that it captures something profound. Others argue that without unique, testable predictions, its connection to nature remains uncertain. Both attitudes reflect an important scientific tension. A theory may be beautiful, consistent, and intellectually fertile, yet still require observational support before it can describe the world with confidence. Hidden dimensions, therefore, occupy a delicate position. They are not arbitrary fantasies, because they arise naturally in serious attempts to reconcile quantum mechanics with gravity. They are also not established facts, because nature has not yet revealed unmistakable evidence for them. For now, they remain carefully constructed possibilities, shaped by equations, constrained by observation, and suspended just beyond the edge of what experiments can reach. The next question is whether our entire visible universe might itself be one surface within a larger dimensional realm, and what such a possibility would mean for gravity, cosmology, and worlds we may never directly touch. Imagine, for a moment, that everything you have ever seen belongs to a surface, not a thin sheet floating somewhere inside ordinary space, but a three-dimensional domain embedded within a larger geometry. Stars, planets, light, atoms, and living bodies might all be confined to this domain, unable to move in the additional direction surrounding it. Physicists call such a structure a brane, a shortened form of membrane. A brane can have different numbers of spatial dimensions, and the hypothetical brane containing our universe would need at least the three large dimensions we experience. Beyond it could lie a higher dimensional region known as the bulk, present everywhere and yet inaccessible to most familiar matter. The image of a sheet in a room can help at first, but it must be handled gently. Our universe would not necessarily be a flat layer with empty space visibly above and below it. The brane itself could contain curved spacetime, galaxies, and the entire observable cosmos. The bulk would differ from our world by direction rather than by ordinary distance. You could travel billions of light years toward the edge of the observable universe and still remain on the same brane. Just as a creature confined to Earth's surface can travel around the planet without moving directly away from it. The missing route would not lie beyond the horizon. It would be perpendicular to every direction available within our universe. A simple analogy is a tiny insect living on a broad sheet of fabric. The insect can move across the cloth but cannot leave its surface. To it, the sheet is the complete arena of motion. A sound or vibration may travel through the fabric in ways the insect can detect, while the surrounding room remains hidden. Now replace the two-dimensional fabric with a three-dimensional brane and the room with a higher dimensional bulk. We would be like the insect, except our accessible world contains volume rather than surface area. The analogy is imperfect, but it captures how a world can be complete from within while still forming part of a larger structure. Why would ordinary matter remain trapped on the brane? In some theoretical models, the fields associated with particles such as electrons, quarks, and photons are bound to it by the underlying physics. These particles are not choosing to stay within three dimensions. Their very existence may be defined by states that live only on the brane. Asking why an electron does not step into the bulk could then resemble asking why a ripple on a pond does not continue upward as the same ripple after leaving the water. The wave belongs to the medium that supports it. Ordinary matter may similarly belong to the dimensional structure that supports its fields. Gravity may be different. In many brane world models, gravity is associated with the geometry of the full, higher dimensional space-time. Gravitational influence could therefore move through the bulk, even when light and matter remain confined to the brain. If so, gravity might spread into more directions than the other forces. Its apparent weakness could result partly from this spreading. Electromagnetism, held close to our brain, would remain concentrated, while gravity would disperse through a larger space. What seems to be an enormous difference in fundamental strength might reflect unequal access to hidden dimensions. The idea is attractive because gravity truly is much weaker than electromagnetism at the scale of particles. A small magnet can lift a paperclip despite the downward pull of the entire Earth. The electromagnetic force between two elementary charged particles is vastly stronger than their gravitational attraction. This gap is known as part of the hierarchy problem. Extra-dimensional models offer one possible explanation, though not the only one. Gravity may appear weak because we observe only the portion remaining near our brain. Its full higher-dimensional strength could be greater, with much of its influence extending into a region ordinary instruments cannot directly enter. If gravity can enter the bulk, its behavior might change at short distances. In 3 spatial dimensions, the gravitational influence of an isolated mass spreads over the surface of an expanding sphere. As the sphere grows, the same influence is distributed across a larger area, leading to the familiar inverse square law. With additional accessible dimensions, gravity would spread more rapidly because there would be more directions available, at sufficiently small scales, before the hidden dimensions become effectively invisible. The force might weaken with distance according to a different rule. Precision experiments have searched for this change by measuring tiny gravitational attractions across very short gaps. These experiments are difficult because gravity is extraordinarily faint between laboratory-sized objects. Electrical charges, magnetic contamination, vibrations, temperature changes, and even subtle properties of nearby surfaces can overwhelm the signal. Researchers therefore use carefully isolated equipment, often involving torsion balances or microscopic mechanical systems. So far, measurements have not found a reliable departure from known gravity at accessible distances. The results place strong limits on large extra dimensions, but they do not exclude every possible model. A hidden dimension could be smaller than current experiments can probe, shaped in a complicated way, or coupled to matter too weakly to reveal itself through these tests. Not all brain world models rely on large, flat extra dimensions. Some imagine a bulk whose geometry is strongly warped. In such a space, distances and energy scales can change dramatically as one moves along the hidden direction. The surrounding geometry may guide gravity toward our brain, allowing it to behave normally over large distances, even while extending into the bulk. Warping can create enormous differences in observed physical scales without requiring equally enormous differences in the underlying parameters. This is one reason extra-dimensional theories remain mathematically interesting. Geometry can perform tasks that would otherwise require unexplained numerical coincidences. The word brain may also suggest that our universe could move, bend, or vibrate within the bulk. In some models, the brain has tension, somewhat like a stretched membrane, and fluctuations in its position could appear as fields or particles to observers within it. Its motion might have influenced the early universe, perhaps contributing to periods of rapid expansion or other cosmological events. These proposals are speculative and highly dependent on the details of each theory. No observation has established that cosmic history was driven by brain motion. But the models provide new ways to think about how geometry and matter might have interacted when the universe was young. Once one brain is imagined, it is natural to ask whether others could exist. A higher dimensional bulk might contain several brains, each supporting its own particles and forces. Another brain could be extremely close in the hidden direction while remaining unreachable through ordinary space. From our perspective, its matter might be invisible because its light would be confined to its own domain. Yet gravity, if able to cross the bulk, might create a faint interaction between the two. This possibility is sometimes associated with parallel worlds, but the phrase can be misleading. These would not necessarily be alternate histories containing different versions of familiar people. They would be separate physical regions within a proposed higher dimensional geometry. Popular stories often blend several distinct ideas under the label parallel universes. One idea involves distant regions beyond our observable horizon, still within ordinary spacetime. Another comes from quantum interpretations in which possible outcomes are described through branching states. A third arises from cosmological inflation, which may produce many expanding regions with different conditions. Brane world scenarios are different again, suggesting separate lower dimensional domains embedded within a common bulk. These concepts may share a sense of multiplicity, but they emerge from different equations and should not be treated as interchangeable. Evidence for one would not automatically confirm the others. Could another brane collide with ours? Some cosmological models have explored this possibility. A collision between branes might release energy into our universe, perhaps producing a hot, dense state resembling the beginning of conventional Big Bang evolution. In cyclic versions, such encounters could happen repeatedly over immense periods. These ideas offer alternatives to certain inflationary scenarios, but they face demanding questions. They must reproduce the observed patterns in the cosmic microwave background, explain the formation of structure, and remain consistent with all other cosmological evidence. No brane collision model has been confirmed as the origin of our universe. The cosmic microwave background provides one of the most precise windows into the early cosmos. Its tiny temperature variations record the seeds from which galaxies later formed. Any successful higher dimensional cosmology must account for the scale, distribution, and statistical character of these variations. Researchers search for patterns that might distinguish one theory from another, but many proposed signatures can be subtle or shared by several models. A curious pattern in the data is not enough. Scientists must ask whether ordinary processes, instrument noise, or statistical chance can explain it before invoking hidden dimensions. Black holes could also behave differently in a brane world universe. A black hole formed from matter on our brane might extend into the bulk, acquiring a higher dimensional shape that cannot be fully represented in familiar space. Small black holes, if they could be produced, might lose energy differently or decay into both brane-bound particles and bulk modes. Particle accelerators have searched for unusual events inspired by these models. None has provided evidence for microscopic black holes or extra dimensions. The absence of such signals has ruled out or constrained some of the more accessible possibilities. Contrary to occasional public fears, accelerator searches for hypothetical microscopic black holes were not expected to create enduring cosmic threats. In relevant models, such objects would decay almost immediately through quantum processes. Nature also produces cosmic rays with energies exceeding those of human-made accelerators, and these particles have struck planets, stars, and other objects for billions of years without observable catastrophe. The scientific interest lies not in opening a doorway to another universe, but in detecting distinctive particle patterns that might reveal how gravity behaves at extremely small scales. Gravitational waves offer another possible way to investigate higher dimensional space. If gravity can travel through the bulk, some gravitational energy might leave our brane or return in altered forms. Extra dimensions could affect how waves propagate, how rapidly they weaken, or what vibration modes are possible. A higher dimensional gravitational field may contain polarizations beyond those predicted by general relativity in four-dimensional spacetime. Detectors can test the arrival times, shapes, and polarizations of signals from merging black holes and neutron stars. So far, observations have remained broadly consistent with general relativity, providing additional constraints without eliminating every hidden dimensional theory. Cosmology also tests whether gravity behaves normally across enormous distances. The expansion of the universe, the motion of galaxies, gravitational lensing, and the growth of cosmic structure all depend on gravity. A theory allowing gravitational influence to leak into extra dimensions must still reproduce these observations. Some models attempt to explain the accelerating expansion of the universe without introducing dark energy in its usual form, suggesting instead that gravity changes across cosmic scales. Such proposals are intriguing, but many have difficulty matching the full range of data or avoiding theoretical instabilities. Dark matter is sometimes linked casually with hidden dimensions, but no such connection has been established. The unseen mass inferred from galaxy rotation, lensing, and cosmic structure may consist of new particles living on our brane. It might also involve a more unusual sector of physics, possibly influenced by higher dimensional geometry. Yet extra dimensions do not automatically explain dark matter, and dark matter observations do not automatically imply a bulk or neighbouring brane. These remain separate mysteries that some theories try to connect. Scientific care requires preserving that distinction until evidence supports a shared explanation. There is a deeper lesson in the brane world picture. Even before we know whether it is true, the limits of our universe may not look like walls or edges. They may be restrictions built into the behaviour of matter itself. A photon could travel across the cosmos for billions of years and still remain confined to the same dimensional domain. An electron might explore every reachable place without ever entering the bulk. What appears to be the entirety of space may instead be the entire space available to the particles from which observers are made. This creates an unusual form of humility. We normally imagine hidden places as distant, dark, or concealed behind obstacles. A higher dimensional region could be none of these. It might surround and intersect every point of our experience, while remaining inaccessible because no familiar path leads toward it. Another brane could be closer than the thickness of an atom in the hidden direction, yet farther from practical contact than the most distant visible galaxy. Nearness would lose its ordinary meaning because distance depends on which dimensions a traveller can enter. And so the possibility of parallel branes remains quiet rather than dramatic. There is no confirmed neighbouring universe pressing against ours, no observed gravitational message from another world, and no experimental doorway into the bulk. What exists is a set of mathematically serious models, motivated by real problems in gravity and particle physics, and increasingly restricted by careful measurements. The hidden realm may be vast, tiny, warped, or absent entirely. To move beyond possibility, scientists must search for traces, missing energy, altered gravity, unusual particles, changed gravitational waves, or patterns in the cosmos that ordinary four-dimensional physics cannot explain. If hidden dimensions exist, they must leave some trace in the world we can measure. The trace may be extremely faint, perhaps buried beneath ordinary physical effects. But science can advance only when an idea risks being contradicted by evidence. This is what separates a physical hypothesis from a story that can explain anything after the fact. A theory of extra dimensions must tell us where to look, what pattern to expect, and how that pattern would differ from the predictions of established physics. The search therefore moves across many scales, from delicate laboratory measurements performed over fractions of a millimetre to observations of galaxies, black holes, and gravitational waves crossing billions of light years. One of the most direct approaches is to test gravity at very short distances. Newton's inverse square law has been confirmed with extraordinary precision across many familiar scales, from falling objects to planetary motion. Yet, if gravity can spread into additional dimensions, its behaviour might change below the size of those dimensions. Researchers place small masses close together and measure the tiny attraction between them, while carefully reducing electrical forces, magnetic effects, vibrations, and thermal noise. The experiment may resemble a quiet mechanical balance, but its sensitivity must be remarkable. Even a faint static charge can overwhelm the gravitational signal. So every surface, movement, An environmental disturbance must be understood. So far, these measurements have not revealed a convincing deviation from ordinary gravity. This negative result is scientifically valuable. It means that certain extra dimensions cannot be as large or as strongly coupled as some early models allowed. The permitted possibilities are pushed towards smaller scales, weaker effects, or more complicated geometries. Science often progresses in this way, not through sudden discovery, but through the gradual closing of doors. Each carefully confirmed absence narrows the space in which a hidden structure might still exist. The universe remains mysterious, but the mystery becomes more disciplined, confined by the quiet pressure of measurement. Particle accelerators provide another route. When protons collide at extremely high energies, their internal quarks and gluons create a brief concentration of energy in a tiny region. If extra dimensions become important at such scales, the collisions might produce unfamiliar particles or patterns. A particle could carry momentum into a hidden dimension, appearing to detectors as missing energy. Alternatively, ordinary particles might have heavier partners corresponding to motion through compact dimensions. These Kaluza Klein states would resemble known particles in some properties while possessing larger masses. Their appearance would be a striking clue that an unseen direction contributes to their behavior. Missing energy, however, is not unique to extra dimension. Neutrinos can pass through detectors with little interaction, carrying away momentum that must be reconstructed indirectly. Hypothetical dark matter particles could do the same. Imperfect measurements can also imitate a missing energy signal. Physicists therefore examine the full pattern of each collision, the directions, energies, and types of particles produced, along with how often similar events occur. A genuine discovery would need to match a specific theoretical prediction and survive comparisons with ordinary explanations. No reliable accelerator signal has yet required hidden dimensions, and many accessible versions of these models have been strongly constrained. Some theories predicted that high-energy collisions might create microscopic black holes if gravity becomes much stronger at very short distances. Such objects would not resemble the massive black holes found in space. They would be unimaginably tiny and, under the assumptions of these models, would decay almost immediately into showers of particles. Scientists searched for the unusual energy distributions expected from such decays. None were found. This result does not prove that microscopic extra dimensions are absent, but it tells us that they do not make gravity strong enough at energies reached so far to produce these predicted events. Another possible signature comes from the energy levels of particles themselves. If a compact dimension exists, motion around it may be quantized. The resulting sequence of states could appear as a ladder of heavier particles, with masses following a characteristic spacing. Detecting one unfamiliar particle would not be enough. Researchers would look for a family of related states and for decay patterns consistent with the geometry of the hidden dimension. Such a pattern would be difficult for an unrelated theory to imitate. Yet no clear Kaluza-Klein tower has appeared in accelerator data, leaving the simplest observable versions beyond current evidence. Precision measurements at lower energies can sometimes probe physics that high-energy machines cannot reach directly. Atomic clocks, particle magnetic moments, rare decays, and subtle violations of known symmetries may reveal the influence of hidden structures through tiny shifts. A virtual particle need not be created as a long-lived object to affect a measurement. Quantum fields allow short-lived fluctuations to influence the properties of familiar particles. If extra-dimensional states exist, they might slightly alter these predictions. The challenge is that standard quantum calculations are already extremely precise, and experimental uncertainties must be reduced until any discrepancy becomes both statistically compelling and theoretically meaningful. Cosmic rays offer natural experiments at energies that can exceed those produced by human accelerators. These particles, often protons or atomic nuclei, strike Earth's atmosphere and generate cascades of secondary particles. If hidden dimensions modify high-energy interactions, unusual showers might appear. Yet cosmic ray events are more difficult to control than laboratory collisions. The original particle's identity and exact energy may be uncertain, and the interaction occurs high in the atmosphere rather than inside a carefully designed detector. Cosmic rays broaden the search, but any apparent anomaly must be interpreted with great caution. The universe itself is an even larger laboratory. The early cosmos was far hotter and denser than anything humans can reproduce. If extra dimensions influence particle behavior, gravity, or the expansion of space, traces might remain in the cosmic microwave background. This ancient radiation carries a pattern of tiny temperature differences across the sky. Those variations reveal the conditions from which galaxies eventually grew. A higher dimensional model must reproduce their measured distribution, their correlations across different angular scales, and their polarization. Many elegant ideas become difficult to sustain when confronted with the detailed structure of this primordial light. Hidden dimensions might also affect how cosmic structure forms. Gravity guides the growth of galaxies and galaxy clusters from small early density variations. If gravitational influence leaks into a bulk or changes across large distances, the rate of this growth could differ from general relativity. Astronomers compare several kinds of evidence: galaxy motions, gravitational lensing, the clustering of matter, and the expansion history of the universe. A valid model must fit all of them at once. Explaining one curious observation while damaging several successful predictions would not be progress. The universe demands consistency across scales and across independent methods. Gravitational lensing is especially useful because it maps the influence of gravity without requiring the gravitating matter to emit light. Massive objects bend spacetime, altering the paths of light from more distant galaxies. By measuring these distortions, astronomers infer how mass is distributed. A theory with extra dimensions may predict a different relationship between visible matter, space-time curvature, and the growth of structure. Yet dark matter, ordinary astrophysical complexity, and measurement uncertainty can produce overlapping effects. For this reason, lensing data must be combined with other observations before any deviation can be interpreted as evidence of higher dimensional physics. Gravitational waves provide a newer and unusually direct test. In general relativity, these waves have specific properties, including the way they travel and the polarizations they can possess. Extra dimensions may introduce additional polarization modes or allow some energy to escape into the bulk. They might also alter the waveform produced during the collision of black holes. Detectors compare observed signals with detailed theoretical templates, following the orbit, merger, and final vibration of the resulting object. So far, the waves agree impressively with four-dimensional general relativity. Although measurement precision continues to improve, the speed of gravitational waves also matters. A signal from two merging neutron stars was observed in both gravitational waves and electromagnetic radiation. The near-simultaneous arrival over a vast cosmic distance showed that gravity and light travel at extremely similar speeds under those conditions. This result constrained several modified gravity models, including some involving extra-dimensional effects. It did not eliminate every brane world or higher dimensional theory, because different models predict different behavior, but it demonstrated how one distant event can close large regions of theoretical possibility through a simple comparison of arrival times. Black holes may preserve other clues. After two black holes merge, the final black hole settles by emitting a sequence of fading vibrations known as ringdown. In general relativity, the frequencies and decay rates depend mainly on the black hole's mass and spin. A higher dimensional object could support different modes or lose energy in unfamiliar ways. Future detectors may observe these signals with enough precision to perform a kind of gravitational spectroscopy. Scientists could compare several ringdown tones, much as one identifies an instrument by its harmonics. Any persistent mismatch would be deeply interesting. Though ordinary modelling errors would first need to be excluded, very small black holes, if they had formed in the early universe, might also test dimensionality. Their evaporation rate and particle emission could differ if additional dimensions were available. Astronomers have searched for radiation that might come from evaporating primordial black holes, but no confirmed signal has appeared. The limits depend on assumptions about how such black holes formed, how common they were, and what particles they would emit. As in many searches, the absence of evidence removes some possibilities while leaving others intact. The deeper theory remains unconfirmed, but less unconstrained than before. Some researchers also study whether fundamental constants could change over time. The size or shape of compact dimensions might influence particle masses or force strengths. If those dimensions evolved, even slowly, the effects might appear in atomic spectra from distant galaxies, in ancient geological records, or in highly precise laboratory clocks. Current measurements place strong limits on many kinds of variation. This suggests that any hidden dimensions affecting these constants must be extremely stable today. Their geometry, if real, cannot wander freely without leaving traces that observations would already have revealed. There is a temptation to treat any unexplained signal as a doorway to extra dimensions, a surprising particle event, a mismatch in cosmic expansion, or an unusual gravitational waveform may seem to invite the most exotic interpretation. Yet scientific history teaches patience. Many anomalies disappear when instruments improve, data increase, or overlooked ordinary effects are included. Others survive and become genuine discoveries, but only after repeated confirmation. Hidden dimensions would represent a profound change in our picture of reality, so the standard of evidence must be equally profound. The strongest discovery would emerge from several independent directions at once. Perhaps an accelerator would reveal a sequence of heavy states, while short-range gravity experiments found a matching change in force behavior. Perhaps gravitational waves would display an extrapolarization, and cosmological data would point to the same dimensional scale. When different instruments, methods, and parts of nature converge on one explanation, confidence grows. A single ambiguous signal may invite speculation. A network of consistent evidence can transform speculation into knowledge. It is also possible that hidden dimensions lie forever beyond direct experimental reach. If they are compactified near the Planck scale, the required energies may be unattainable with any realistic machine. Scientists might still infer them indirectly if a theory produces unique low-energy predictions. But if many different hidden geometries lead to the same observable world, testing the idea becomes much harder. This challenge lies at the heart of current debates. A theory may unify equations beautifully while leaving too many versions compatible with what we see. Even so, the search is not empty. The mathematics developed for extra-dimensional theories has deepened understanding of quantum fields, gravity, black holes, and geometry. Dualities have revealed surprising connections between apparently different physical descriptions. Ideas inspired by strings and branes have provided tools for studying strongly interacting systems and the thermodynamics of black holes. A theory can contribute valuable insight even before its most ambitious claims are confirmed. Yet usefulness and truth remain different questions, and physicists continue to hold both in view. For now, every careful measurement returns us to a universe that behaves remarkably well as four-dimensional spacetime across the scales we can test. The hidden directions, if present, remain concealed behind smallness, weakness, warping, or confinement. They have not announced themselves through altered gravity, missing energy, new particle towers, or unmistakable cosmic patterns. But the silence is not complete emptiness. It is a boundary being mapped, an increasingly precise description of where new physics cannot easily hide. And perhaps this is the calmest form of exploration. There is no need to force an answer from nature. Instruments listen. Equations make their predictions. And observations slowly separate possibility from reality. Hidden dimensions may eventually emerge as part of the universe's architecture, or they may fade into the history of beautiful ideas that guided science towards something else. Either outcome would deepen understanding. The purpose of the search is not to preserve the mystery, but to approach it honestly, allowing the universe to decide which of our imagined directions truly exist. After traveling through curved spacetime, compact dimensions, strings, branes, particle accelerators, and gravitational waves, we arrive at a place where science becomes quiet again. The central question remains open. Space may contain hidden dimensions, or the mathematics may be pointing toward a different structure that we have not yet learned to describe. No experiment has confirmed an extra spatial direction, and no observation requires one beyond doubt. Yet the possibility has changed the way physicists think about reality. It has shown that the space surrounding us may not be a simple emptiness, but a physical structure whose full depth could remain concealed beneath the scale of ordinary experience. Our senses present a world of three large spatial directions because that is the world in which bodies move. Objects fall, and light reaches our eyes. This picture is reliable within its proper range. It guides us safely across rooms and landscapes, and it allows engineers to build bridges, aircraft, and instruments of astonishing precision. But science has repeatedly shown that a useful picture need not be the final one. Solid matter is mostly open space structured by quantum fields. A motionless landscape is carried around a rotating planet. The universal flow of time gives way to clocks that tick differently depending on motion and gravity. The universe is not required to remain simple merely because simplicity is comfortable to us. A hidden dimension would not make daily life unreal. The familiar world would still exist as an effective description. Just as the smooth surface of water remains real even though it is composed of restless molecules, different levels of nature can be true at the same time. A table can be solid enough to support a book, while its atoms are described by quantum probabilities. Earth can feel flat across a quiet field, while its surface curves around a sphere. Three-dimensional space may be complete for human-scale movement, even if it emerges from or rests within a larger geometry. This idea of emergence may be one of the deepest lessons offered by modern physics. Some properties that appear fundamental at one scale may arise from relationships at another. Temperature emerges from the collective motion of particles. The elasticity of a material emerges from the arrangement of atoms. A wave on the ocean has a shape and speed of its own, though it is made from countless water molecules following local forces. Perhaps space itself is similar. Its dimensions, distance, and smooth continuity may emerge from more basic quantum connections that do not resemble space in the ordinary sense. Several areas of theoretical physics now explore this possibility. In some mathematical relationships, a gravitational theory within a volume can be equivalent to a quantum theory defined on its lower dimensional boundary. This idea is known broadly as holographic duality. The name suggests that information describing a higher dimensional region may be encoded in a lower dimensional system, somewhat as a hologram stores the appearance of depth on a surface. The comparison is imperfect, and the best understood examples do not directly describe our observed universe. Still, they suggest that dimensionality may be more flexible than it appears, and that a space with gravity could emerge from physics formulated with fewer dimensions. If that is true in nature, the question may not simply be how many dimensions the universe has. We may also need to ask when and how dimensions become meaningful. At extremely small scales, the smooth idea of location could dissolve into a network of quantum relationships. Space might not be a container in which these relationships exist. Instead, the container itself might arise from them. Distance could measure how strongly parts of a quantum system are connected. Geometry could emerge gradually, like the outline of a landscape appearing through mist, becoming clear only when many microscopic elements act together. This possibility does not erase the search for compact dimensions or brane worlds. It places them within a broader question about what space truly is. A hidden dimension might be a literal direction curled too tightly to observe. It might be a large direction inaccessible to ordinary matter. It might exist only in a mathematical description equivalent to another theory with fewer dimensions. Or, dimensionality itself might depend on energy scale, appearing different when nature is examined more closely. These ideas are not all compatible, and none has been confirmed as the final account. They show how many forms the mystery can take once ordinary intuition is no longer the only guide. There may also be strict limits on what human beings can ever know. The observable universe is finite because light has had only a limited time to reach us. Regions beyond our cosmic horizon may remain permanently inaccessible if the expansion of space keeps them from ever sending signals here. The Planck scale may lie so far beyond experimental reach that no accelerator built from realistic materials could probe it directly. Some theories may produce nearly identical observable predictions, making them difficult to distinguish. Nature may contain truths that are real, yet hidden not only by present technology, but by the structure of physical law itself. This does not make investigation meaningless. Knowledge has never required access to everything at once. We cannot enter the center of the sun, yet we understand its interior through light, neutrinos, vibrations, and physical theory. We cannot watch the early universe directly, yet ancient radiation preserves information about it. We cannot see atoms with unaided eyes, but their effects create patterns that instruments can measure. Science often studies the invisible by examining what the invisible allows, prevents, or changes. Hidden dimensions, if they exist, may eventually be known in the same indirect way. Perhaps a future experiment will discover an unexpected sequence of particles whose masses reveal motion through a compact direction. Perhaps a new gravitational detector will identify a polarization that four-dimensional relativity cannot produce. Perhaps measurements of gravity at microscopic distances will reveal a subtle change in how force spreads. Or perhaps every test will continue to agree with a universe containing only the familiar dimensions, while a different theory succeeds where extra-dimensional models do not. Scientific progress does not promise a particular answer. It promises a method for becoming less wrong. Theories themselves may also change beyond recognition. General relativity transformed Newton's gravitational force into curved spacetime. Quantum mechanics replaced definite classical motion with amplitudes and probabilities. A future theory of quantum gravity may preserve aspects of strings, branes, loops, holography, or ideas not yet imagined, while reorganizing them into a new language. The extra dimensions discussed today may then appear as fundamental realities, useful approximations, or mathematical shadows of something deeper. Scientific concepts are not defeated when they become part of a larger theory. Often, they survive within it, gaining clearer boundaries and more precise meaning. There is a gentle humility in recognizing that the universe was not designed for effortless human understanding. Our brains developed within a narrow range of size, speed, temperature, and gravity. We are comfortable with falling stones, moving animals, familiar faces, and distances that can be crossed in a lifetime. We did not evolve to picture 10-dimensional geometry, quantum superposition, or space-time near a black hole. Yet through language, mathematics, observation, and shared effort, the mind can reach beyond the conditions that shaped it. We may not visualize hidden dimensions directly, but we can trace their possible consequences with reason. That ability is itself part of nature. The equations written on a page, the mirrors inside a gravitational wave detector, the cooled sensors beneath a laboratory, and the quiet thoughts of someone listening at night are all arrangements of matter produced by the same universe they seek to understand. The cosmos is not being observed from outside. A small region of it has become capable of asking what space is made of. Through human curiosity, matter studies geometry, time measures itself, and the universe forms questions about dimensions that may lie beneath its own visible surface. This perspective can make our smallness feel less like insignificance. The observable universe contains hundreds of billions of galaxies, each filled with stars separated by distances almost impossible to imagine. If hidden dimensions exist, then even this enormous visible expanse may represent only part of the full structure of reality. Human life occupies a brief moment on a small planet around an ordinary star, yet size is not the only measure of meaning. A quiet mind can hold an idea wider than its body, and a short-lived civilization can detect waves from black holes that merged before Earth existed. The search for hidden dimensions also reminds us that absence can be profound. We do not see the extra directions. We do not feel them opening beside us. We have not found their particles or measured their unmistakable effect on gravity. Still, the unanswered question creates a space for careful thought. It invites us to distinguish what is possible from what is proven, what is elegant from what is true, and what we imagine from what nature reveals. This discipline does not reduce wonder. It gives wonder a stronger foundation, allowing mystery to remain without filling it prematurely with certainty. Tonight, the room around you continues to appear simple. There is distance between the walls, height above the floor, and a quiet sequence of moments passing through the dark. Nothing in ordinary experience announces a fifth direction curled around every point, or a larger bulk surrounding the visible universe. And perhaps there is none. But the calm surface of space does not tell us everything about its origin, its smallest structure, or the deeper laws from which it may emerge. The familiar world may be complete at our scale while still resting upon a reality more intricate than perception can show. You might imagine space now not as an empty box, but as a soft question extending in all directions. Every star occupies a position within it. Every beam of light follows its geometry. Every atom in your body exists according to laws that may be connected to structures far below the reach of sight. Whether hidden dimensions are real or only stepping stones toward another theory, they have led us toward a more careful appreciation of the unknown. The darkness between objects is not necessarily nothing. It may be geometry, possibility, and unanswered structure. And as this journey comes to its end, there is no need to solve the mystery tonight. The universe has carried its dimensions for billions of years without requiring us to name them. Experiments will continue. Equations will be revised. And future observers may understand what remains hidden from us. For now, it is enough to rest within the space we know. 3 broad directions. 1 flowing time. And a quiet horizon of questions beyond them. Around you, the world remains steady. Beyond perception, reality keeps its secrets, and beneath the gentle silence of the night, the universe continues to be deeper than it appears.